Okay, so now we are doing today's daily code problem, which is minimum time to collect all apples in a tree submission, right? Okay, not tree submission, but it's remove submission from here. Let's give description. So this is a basically graph problem that I can tell you that okay, apples in a tree, but this you have been given a tree in format of graph. So it's not like just a binary tree. It's kind of an n-ary tree, but I don't know like how many edges can be there, how many, you know, you have been given a directed tree of n vertices, right? 0 to n minus 1 vertices. You should spend 1 second to walk on one edge. Return the minimum time in seconds that you need to spend to collect all the apples starting at the vertex 0 and coming back to the vertex 0. Try the edges undirected are given in the array edges. AI is equal to AI, bi means that it exists an edge connecting the vertices AI and bi. Additionally, there is a boolean array which has apple, which represent whether this particular vertex has an apple or not. If it's true, it has an apple. Otherwise, it doesn't have an apple. Now what you need to return is basically a number, something like how much, time that you need to come to start from 0. Return the minimum seconds you start from 0 and then come back after visiting all the vertex to the 0, right? After collecting all the apples starting at vertex 0 and coming back to the same vertex. So how you can do this? Now, this problem is basically a typical not backtracking, but this problem is basically post order traversal problem, where you have to calculate answers for children before calculating the answers for the node or parent itself. So for example, like 0 1 2 4 5. One way is, you can say, okay, I'm standing on 0, whether 0 has an apple or not, right? Whether 0 has an apple or not. So currently 0 doesn't have an apple. So you'll say, okay, currently my, t is equal to apples is equal to 0, right? Now you know that 0 doesn't have apple. So will you stop at this point? No, you have to check the whole graph now. So you have to check whether 1 has an apple or not. Now 1 doesn't have an apple. Still a is equal to 0, and time is basically you have vertices, just you have just visited 1 from starting from 0, and then you will say, okay, now 1 doesn't have an apple. So you can't do anything about it. You will just move to children's 4 and 5. 4 has an apple. Now 4 has an apple. You'll say a is equal to now 1. So how can you, tell that, okay, I found the apple at two distance? Maybe you can do a kind of, just DFS, where you say 0 goes to 1, 1 goes to 4, and you can keep track of that timing when this first of all this first vertex gets an apple. So at this time is equal to 2. If you say time equal to 1 at 0 second, sorry, 0 at 0 second, 1 at 1 second, now at the 4 second, its time is a time value. How we do time marking kind of question. So we can do that it as well, like mark 4 as a timestamp as 2, and I'll say, okay, I'll get first apple at timestamp equal to 2. And then I will go on again, like how the DFS happens. You can check the is there any node after this. You'll say, okay, no, there's no any node after this. You'll say, okay, now go back to your parent, which is 1. So timestamp is now 3, and then it will go to 5. A is equal to 2. You have collected 2 apples. Timestamp equal to 5. You can't go more down. You have to go up from this, like timestamp is equal to 6. You will come back to this 1, 2, 3, 4, and 5. Timestamp is equal to 5. You are standing on 1 and going backwards, right, to 0. Timestamp equal to 6. You are coming on 0, and then you will go for 2. It is having an apple. You'll say a is equal to 2. Timestamp is equal to 7. 5 here, 6 here, 7 over here. Fine. Now what you'll do? Will you directly go back to 0? No, because you have a tree left. So you'll go to 3. You'll say no, apples are there. So a is still equal to 0. Time is being increased to 8. Then you'll go back to 2. Time is 9. You'll go to 6. You'll check no apple. Apple is still 2. Not 2. How the okay? Apple was 3. Yeah, over this point. So at this time value was something like 7, 8, 9, and then 10. And then you'll say, okay, now go backwards again, because 3 and 6 doesn't have any children. If they would have children, so it would go searching all that. And when you return, timestamp would be, for last 0. It is actually fixed. Whatever you will do, it is fixed, and this fixed value is equal to the complete traversal of the tree. But that's not what you want now. You can do complete traversal and you will get all the apples that you want, but that's not the minimum time now, because you can take back route from this 2 as well. Why you need to check 3? But then there is also a need for checking 3, because the 3 can have apple or cannot have apple. So how do I know whether from this vertex 2 should I move down, or should I just make a u-turn? and go back to zero. This is the whole point of this question. Otherwise, the answer would be the whole DFS traversal time for the node, right? For the node zero. But that's not the answer, because you have to, move smartly. Like, let's say four has a children, like say 8 and 9, and five has a children like 10 and 12. But we don't need to go there because they don't have apples, right? So we just make a U-turn from this four, go to five, make a U-turn from this five, and then go back. How do you know that you have to make a U-turn, and how do you represent that in the value of, traversal time, how much distance you have walked, or how much time you have taken, or what is the value that you are returning? This is the whole idea, and that's why you cannot, do something like pre-order or in-order kind of thing. You have to do post-order. So you are not checking for zero, you're not checking for one, you're just checking for four. You are not even checking for four. You are going down till it is possible. Like, let's say 0 1 4 is there, 0 and 1 is there, and 4 is there, and let's say 8 and 10 are children of this four, like, let's say, and they are in this form, like 8 and 10, and there is no children on the right hand side. Let me make it like this. And something like one has two children, 4 and 5, and zero has two children, 1 and 2, and currently two is having this 3 and 6. Or you can extend this also. What I'm saying, you will you'll start from zero, you'll say okay, go back to one, and don't calculate anything for one. You go to four, don't say that you have an apple, and do plus anything, don't do that. You just go to for 8, then you just go to 10. 10 doesn't have apple, so let me tell you which having an apple. So 4 is having an apple, 5 is also having an apple, and then 2 is having an apple, right? So this is the same thing. So after 10 you'll see, okay, do you more to go? Do you have any children? You'll say no, I don't have any children, I don't have anything to go. Whether, or now you'll say, okay, whether you are an apple or not, then I can do plus 2 for you or not. So he'll say, I'm not an apple. So what you'll do, okay, you'll return 8 that don't need to go there, don't need to go down, because the 10 is not an apple. Let's say if there was 11, then you earn 11 is an apple, right? So 10 will say, okay, I'm not an apple. He will return something like 0. 8 will say, okay, this guy is not returning. I have one more child. So you have to check that child also. You have to check all the way down till that point you can check, right? So you'll check for 11. Your 11 will say, I have an apple, right? He'll say first, I don't have any children. So don't go down. Don't need to go down. Just move backwards. But you have an apple. So do a plus 2 for me. Like, I need plus 2. Why I need plus 2? Because going from 8 to 11 is 1, and 11 to 8 back is plus 1 again. So 1 plus 1, that's 2. Or you can just say that I'm visiting one edge. After that, after calculating whole the thing, you just see how many edges I have visited, and then do plus 2 for that. That's also you can do. I can show both the ways, or I can, yeah, let's do the second way. I'm just calculating the edges, and 2, why into 2 for that? Because you are going down and then going up. 2 times you are visiting a particular edge that you need to visit, right? So 8 comma 11, is that an edge that you need to visit? Now you'll say, okay, 8 will say, okay, I have some apples over here, so 8 to 11 edge isn't important, and that's why it is. Let's say if it was not important, it will say, okay, I don't have any apple. So he will say its parent, which is 4, that don't need to go down, just move backwards, just make a U-turn, don't need to check for 8, and don't need to plus any answer for 8. There are no apples down there. But if there was 11, then you need to go. So that's why the children is telling a parent whether you have to take a u-turn, or you have to go down, or you have to just make a u-turn and go back. So that was a whole problem which we were having in the normal traversal. We could not say like two whether should go on three or not. So for that matter, three should have been calculated first, and three should have all the things right in the head, that okay, I have any apple or not, am I any apple or not. So that's why he'll return to, okay, no, I'm not an apple, my children is also not an apple, you can just move backward. So two will say, okay, on the three side, I don't need to do anything. Six will also say that. So two will just make a u-turn. So that's how the problem will proceed. Now let's move to the coding part, DFS part. So into DFS, what it is returning, you are on a particular, let's say, starting vertex, and then you are setting something value to return. The value to return is, let's say, if 8 was having 11 as a child, and 11 was having an apple, you will got down till over here 11. That's what I said, you can return either 0, either 1 or 2. uh no, yeah, 0 or 1, either 0 or 1, or 0 or 2. Like, it depends on you. You want to count edge, or you want to count the total path. Total path is 8, but the number of edges you have visited is 1 2 3 and 4, as you can see. So currently I'm just calculating the edges. You can do path as well, I'll show you that also. So 8 and 11 will say, okay, I have an important edge. 8 comma 11 is an important edge. So 8 has to inform the parent, which is 4, that you have to come down, because there is an important edge from 8 to 11. Even when 4 doesn't have an apple, even when 4 doesn't have an apple, you will it will go down till here. Then you need to visit 4. Why? Just because of this 8 comma 11 edge is important, right? Because 11 has an apple. So that's why this is basically, important value is equal to 0, right? Whether you are important or not. Then for all children, I'll see auto I in G of SV, all the children of this particular node, int is, let's say, are you important or not, something like that. So check for child, check for child, check for check for I, basically it's check for child, or I is child, my thing, so something like that. So check for I will be just dfs of I. Okay, now dfs of I will return me either 1 or 0. 0 means no edge is important down from I. 1 means okay, there are some important edges down from I. It can be the same, it may be like that is just grandchildren of I. For example, 4 will also return something like 1 because there is an important edge, 8 comma 11, right? It will only return 1 because why it will return 1? It will return something like 2 because 8 comma 11 is important edge. It will say okay, I have a children which is important, so 8 comma 4 is also an important edge, so it will return something like 2. That we'll see how it is returning number of edges which are important. So let's say currently I'm standing on 8, and let's say currently I'm standing on 11, so that doesn't have any children. So that's we'll talk about that. So for that you can just return your t, whatever, not t but the important value. So important value for 11 is equal to 0. Okay, that's the thing. 11, important value for 11 is equal to 0. 11 is not checking itself. Who will check 11? 11's parent, which is 8, will check parent. So currently I'm on 8. 8 got answer from 11 as 0, obviously from 10 also 0, but currently I'm seeing 11 because now the important part comes, that if okay, so before that visited also, before doing all this, you have to check whether it's visited or not, or you can just make parent child because it is just 0 to n minus 1 edges. You can make parent child thing, and I'm just going by visited vector. Although it takes some more time complexity, but it's easy to implement as like I think, and that's about it. So it should be not visited, then only you will see that children. Now the thing comes, if this children has an apple, like let's say 8 will see whether 11 has an apple or not, then he will decide. 11 has said okay, nothing important down from me, yeah, because 11 does not have any children, but 8 has to decide whether 11 is important or not. So if 11 has an apple, so I'm creating another has apple of I will tell me either you have an apple or not. If you have an apple, then I have to include this edge somehow. So I'll say t plus equal to 1. This is how I'll include the edge. So not just t plus equal to 1. uh hmm, this was check for I. Check for I returned something t plus 1 equal to 1 plus check for I, right? So there might be case that when DFS I would also be returning something. Currently it's not returning anything. 1 is 11 is not returning anything, but still I'll do t plus 1, t is equal to t plus equal to just 1 for this apple, and this check for I is 0. So t is equal to currently my 1, and return okay, it's not t, it is important value. Important value is just 1. Okay, now okay, there is just one important edge, 8 to 11. Now it will return 1 to 8. Okay, now 4 will ask from 8. 8 will give him something like this value. This will again run after this. So you have calculated answer as 1 for 8. Now does 8 have an apple? No, 8 doesn't have an apple. So important value is equal to, yeah. Now would you not increment the important value? That's the question. You still have to include the the you have to increment the important value. So there is an or condition. If the current node is an apple, the current children is an apple, or any children of this has an apple, how you'll check? Simply, if check for I is the check for I is returning 1. Now what does this 1 means? That there is any children which is good, which is having an apple. So similarly, if check for I is good, so you'll say okay, then I need to do important plus 1 because this doesn't have any apple, but still it needs to be included for including its children, 11. So that's why 8 is included now. So important plus is equal to 1 plus, so that for what edge? For 8 to 4 wala edge. And what is this plus check for I? Because what is the down from here? The down value from here is 1 because 8 to 11 is also one edge. And I think that's about it. And then you'll return something like 2 from here. So 4 will say okay, there are two edges which are important. 1 will say okay, whether 4 is good or not. 4 will say I'm not good, but I have a check value. Check for I is equal to 2. So he'll say okay, you do not have an apple, but you have check for I equal to 2. So you have to include this edge because there is an important apple. So 1, 4, 8, 11. There are just IMP plus is equal to 1 plus check for I. So 1 plus 2 is equal to 3. So important value for 4 for 1 is equal to 3, right? Now similarly for 5 it will be something like 0 because there is nothing down from here. But he has to important value has to be plus 1, because check for I for this 5 is 0, but this has apple, 5 has an apple, so plus 1 for that. So it would be 4 till now. So one has having something like 4 edges which are required, which 4 edges: 1 to 4, 4 to 8, 8 to 11, these 3, and 1 to 5. These are the 4 edges which are required for you know uh, down from 1. So he'll return that to 0. Check for I for 1 is equal to 4. One doesn't have an apple, but check for I is greater than obviously positive, so you have to do plus 1. So 0 got 5 edges from the one side, that's completely okay, because 0 to 1 and then 4 down from there. And A2 is also returning something like 0, but it's an important, so plus 1 for that. And total answer for this is equal to 6, which is the correct answer indeed. You did not go for every edge, you just calculated all the important edges and do plus 1 for that. I hope it's clear. Let's do this the things which we need. Doing this is something like DFS, obviously DFS calling for 0, and then before that you have to have a graph. I have not created a graph yet, so I'm just using a vector of int of what's say has apple. That's an important thing, and visited is an important thing. And you have a, let's say, graph, vector of integer and graph. So this is the way you can pass it in a function itself as a parameters. Yeah, and then g dot resize n comma, yeah, nothing but just, yeah, for I just need to make a graph for this edges. E g of I of 0 dot pushed back I of 1, and similarly you can say I of 1 dot push back I of 0 undirected. Now resize your visited, resize your has apple. Okay, not just resize your has apple, but yeah, you have to do something for that as well. So has apple will get resized first, and then you can do for not auto int I is equal to 0, I less than n I plus plus. Basically this has apple and this has apple is different. I created like that. You can pass this into this as well, or yeah. But let me pass it. I don't think we need has apple to be created because I already have an has apple. So let's use it. DFS of 0 comma has apple, vector of int comma has apple, and I comma has apple. I think it should be fine. Anything else? I don't think so. Okay, now you don't need to do for that. You can just say has apple. E is undeclared, obviously. E is just E. Wait for some time. DFS has apple is not declared, or DFS is not or return. Use of undeclared variable, DFS. Why is this an undeclared variable? I think that was the problem. What do you mean by undeclared variable? DFS variable? It's a function. Hmm? What's the problem? DFS. Is it not D? Okay, I think that was something else. Now vector of bool. Oh, I converted into vector of int, but ah, deadly signal for what? Why so? G of sp I dot push back of 1 dot push back of 0. Acha, visitor dot resize n comma 0. Oh, I'm not visiting, I think, yeah. Visitor dot sv equal to 1 or 2, whatever. We're just checking for that. Okay, what is this? Why wrong? Oh, that's what I said. I'm calculating the edges. So 2 into the number of edges. So for that total path will be coming out like that. 2 into this. Whew, let's submit this up. Pretty good efficiency. That's about it. Can we do? Okay, let's do GFG in the next video. Okay, guys, bye.